Hello everyone. We are going to commence another webinar conducted by Institute of Physics Sri Lanka. This is the first webinar for the year 2022, and we hope we would be able to continue successfully this year also, as we conducted last year. Thank you for being here today also. We have been organizing this monthly webinar series to promote physics and its applications, and we are the public on hot key topics related to physics. So today's webinar, we have invited Prof.Channa Silva, Associate Professor of Chemistry in the Department of Chemistry and Physics at Western Carolina University, USA. He will talk on heavy metal-based nanoparticles for luminescent applications. On behalf of IPSL, I would like to warmly welcome Professor Channa Silva. Thank you, Professor, for accepting our invitation. Before start the presentation, I would like to call upon Dr. Chathura Nupearachi, co-editor of IPSL, to introduce today's resource person. Thank you very much, and over to Dr. Chathuri.
Thank you so much, sir. And it's my honor and privilege to welcome our resource person for 2022 January webinar. Actually, Dr. Channa Silva is an associate professor of chemistry in the Department of Chemistry and Physics at Western Carolina University, USA. He has completed his BSc degree in chemistry at the University of Kelaniya, Sri Lanka back in 2000, and completed his PhD in chemistry at the University of Arizona in Tucson. He has worked as a research associate at the Pacific Northwest National Laboratory in Washington, USA, and Bio5 Institutes at the University of Arizona, USA from 2008 to 2010. His research is focused on developing metal-based nanometals for potential luminescent applications and computational studies of materials containing heavy metals. Dear ladies and gentlemen, apart from being a professor in his free time, he likes to play music. So over to you, Professor Channa Silva. This platform is yours.
Thank you, Dr. Chathuri, for the invitation, and Professor Gamage. So I assume you all can hear me. Good?
Yes, sir. Yes. You are loud and clear.
Okay. So I would like to take this opportunity to wish you all a Happy New Year with good health and happiness. And I wish all the best with your future careers, future successes. So today I'm going to talk about some nanomaterial applications and how we make these nanoparticles and what kind of characterization that we do. So you may not understand everything I say here, but my point here is to give you an overall idea about what kind of things we can do with nanoparticles and what we do here. So I'm gonna stop my video for a second and then keep talking so you can focus on the slides. If it moves, I think it got stuck. Let's see. Oh, here we go. So nanotechnology, I can give you a definition. It's a very loose definition. What we do is we talk about the technology that deals with science and engineering of materials at dimensions. We are talking about roughly 1 to 100 nanometers in length. You can see a big nanoparticle here, 10 centimeters, and then when you break it down, you can see 1 nanometer particles. So, you know, 1 nanometer is a billionth of a meter. So we are talking about tiny, tiny things here. So we believe the advent of nanotechnology is considered to be the biggest engineering innovation since the Industrial Revolution. So one aspect of nanotechnology is that their surface volume, the surface area is higher. So higher surface to volume ratio. So you can see that in this very simple example, if you take a 20 centimeter by 20 centimeter by 20 centimeter cube, if you break it into 4 10 centimeter by cubes, you increase the surface area 2 times. But if you take the same 20 centimeter cube and if you divide into small cubes with 20 nanometers, you're going to increase the surface area by 100 million times. So you see the power of changing the materials here. Another aspect is if you look at the size of a baseball bat, which is about 1 meter, and if you go to a fingertip, which is about 1 centimeter, and a needle eye is about 1 millimeter, a human hair is about 100 micrometers. That's what you can see with your eyes. And then now we are going down to red blood cells in the nanometer, and also bacteria cells are also in nanometer, 3000 nanometers. And then you were talking about viruses these days. It's a big deal. COVID virus in the nanometer range, 100 nanometers, for example. And if you go down, DNA is even small. We are talking about molecular level there. So nanoparticles sit between these above the nano DNAs, but somewhere in the viruses, bacteria, that range. So the point is, we're talking about very small things. So just to give you an idea, a size of a paper, one printing paper, A4 paper, is about 50,000 nanometers. So you get the idea. So why do we care about nano? You probably have listened to many talks on nano, but what is the big deal? The big deal is the physical properties are highly dependent on their size, their shape, and their morphology, which is a distinct feature of nano-sized materials. So what does that mean? That means if you change the size of this material, you are getting different physical properties, right? Here you see bulk gold is gold color, but if you make them 100 nanometers, 20 nanometers, you see you get different colors. So what you wear, the ring is not nano, okay? So if you go to nano, you get different colors. So what is that? I'm 100% sure you all have learned this concept in physics. The valence bands and conduction bands in materials, you know, the valence band contains electrons. The conduction band is empty. But if you give energy to this material, you can promote an electron from the valence band to the conduction band. We call you excite the material. This can be done by using light, heat, or electricity. So, you know, this is an important concept that, you know, you guys all use computers, cell phones, semiconductor industry is extremely important. So this band gap, that means the gap between the valence band and the conduction band, can be used to classify these materials. If you have a huge band gap, that is an insulator. If it's a very small or almost no band gap, is a conductor, and in between is a semiconductor. So why am I talking about this? Because when it comes to nanomaterials, you can fine tune this band gap by using the same material. You have probably learned about p-n junctions. So my point is that if you take a nanomaterial, the same thing, same material, but if you change the size, you see the band gap is getting bigger when your size is getting smaller. So we are talking about the same material. So isn't that fascinating? So you can fine tune the size so that your band gap is different. So you can observe different colors, different absorption wavelengths, and you can obtain different materials for different applications, right? So that is the beauty of nanotechnology. So this is one example. Cadmium sulfide or cadmium selenide is a heavy metal or quantum dots. It's not just one cadmium atom and one selenium atom, it's a bunch of them. It's a 3D network. But when you control the size of this nanoparticle, you are getting different colors. You can see that the bigger particles, the band gap is smaller, so it absorbs light, low energy wavelength. So that means red light, for example. When the particles are smaller, their absorption is in the purple range. So you can see different colors based on the size, which is a big deal. So that's just one property of nanomaterials. So nanomaterials, nanotechnology is not something new. People have used nanomaterials thousands of years ago in fabric, and as well as in Egyptian history, people used lead oxide nanomaterials to dye their hair. And also ancient Rome, they used silver and gold nanomaterials to make some balls. And if you light a candle, you can see some fluorescent properties. European church windows used silver nanoparticles for different colors. And European knights used blades with steel, which is a nanofibrous structure. So it was known, but here we come back and then we say nano. So what are the physical aspects of these nanoparticles that we study? What are the photophysical properties that we study? You know, I have a lot of friends, colleagues who work in physics groups or do research in the area of physics in national labs in the United States and some universities, some companies. So basically here I want you to focus on three types of things we do. One is what we call the absorption. Probably you have learned this in physics and chemistry. Absorption is a property of a material that when you shine light, it absorbs some sort of energy based on the electronic structure and how the orbitals are placed. And this is connected to the absorbance, which is the absorption property by molar absorptivity. That's a constant. How far the light travels, the path length, and the concentration of the absorbing species. So we measure the absorbance of these materials. So this is a typical curve. Your y-axis is the molar absorptivity or absorbance or intensity, and your x-axis is the wavelength or energy of radiation. Okay, so that's an important property that we measure. And then we talk about fluorescence. We use the word luminescence. So you have heard about fluorescence, phosphorescence. There are different names. So what we do is you have an excited state. That means the electrons in the lower energy levels get excited by absorbing light energy or heat energy. And when they relaxes back, it can emit a photon, which is light, right? So absorbance happens at a higher wavelength. At a lower wavelength, which is high energy. I hope you know the relationship between the energy and the wavelength, which is inversely proportional. So emission or the luminescence comes at a lower energy, which is higher wavelength. So we measure the luminescent properties by absorbing the molecule by exciting electrons. So, and we measure what we call the quantum yield, which is the efficiency of the luminescence process. It is something like if you give 100 photons, which is 100 photons absorbed, and if the material gives 100 photons back, we call your quantum efficiency is 100% or 1. So there is an indirect way of measuring the efficiency of these materials. You use the absorbance and the integrated area of the emission and refractive index of the solvent, and we use a reference, and then you can measure the quantum yield of the sample. So those are the basic three properties we measure: the absorbance, the luminescence, and the quantum efficiency. So we want to develop materials with enhanced luminescent properties so that we can use them for different applications like light emitting diodes, or imaging, cellular imaging, fiber optics. like that. So our work is mainly focused on lanthanides. Lanthanides are elements from lanthanum to lutetium. They are known as rare earth elements, but they are not rare compared to platinum, palladium. So they have F electrons, and which are responsible for their unique optical and magnetic properties. There's a lot of research going on magnetism. There's a lot of physics groups working on magnetic properties, superconductors, things like that. So why lanthanides? I'm going to start talking about the photophysical properties here. So what we do is we have the lanthanide metal and we attach something called a ligand or an organic part or a molecule. We call it a sensitizer molecule, okay, which is an antenna. What it does is it absorbs light and it transfers that energy to the metal center so the metal can emit. So this is something called the forced energy transfer mechanism. So the first step is you give light, you shine light, so the compound, the material gets excited to the singlet level. And if the energy goes down or electron goes down by releasing energy, we call it fluorescence, but that's not what we want. We want it to get excited, and then we want that singlet energy to transfer to the triplet level. We call it intersystem crossing. And the triplet level, if it goes down, it's called phosphorescence. We do not want that either. We want that triplet energy to get transferred to the metal excited states. These are quantum numbers or excited states defined as term symbols. And that's called energy transfer from triplet to the lanthanide excited state. And when it comes down there, we see the lanthanide-based emission, okay? So what we want to do is we want to make a nanoparticle and we want to coat it with the ligand so that we can shine light on the ligand and it absorbs light and it gets transferred to the metal center and the metal gives light off. Believe it or not, nobody has done this with the nanomaterial before us. That is fascinating. So we wanted to give it a try and see whether it works with lanthanides. Other features of lanthanides are their emissions are very narrow. So you see the full width at half maximum is about 15 to 20 nanometers. So the first material is a lanthanide base. This TB stands for terbium. It's a lanthanide. This other piece is the organic part, and it gives narrow emission. Have you heard the word monochromatic? That means pure colors. That's what we observe with lanthanides. Whereas polymers, organic-based polymers, they give broad emission, okay? There are other advantages of lanthanides. You can choose different lanthanides. You can get different colors. These days, scientists are focusing on infrared emitting materials, a huge big deal for some security applications and some imaging type applications. Lanthanides have longer lifetimes in the luminescent process, which is important. And they are photo bleaching. That means you can keep using them without destroying the material for a long time. And their stock shifts are larger. That means your absorbance is far away from the emission, so you don't have interferences there. So I talk about some qualities of lanthanides. The problem so far is any metal-based nanoparticles, the luminescent is very weak. The reason is what we call a selection rule in photophysical properties. One selection rule is that the excitation between the same orbitals, 4f, 4f orbitals in this case, they are forbidden by the selection rules. We call it the parity rule or the Laporte rule. Bottom line is they are not good. So what we do is we use what we call the antenna, and do the antenna effect. That means we use the antenna to excite the molecule, or in other words, for it to absorb the light, and then it transfers energy. So we are trying to make use of that. So now I have talked about some basic introduction, and I'm going to show you some results here to the level that you can understand. So you see, we are working on lanthanides, and these lanthanides can be embedded in different matrices, different materials like lanthanum fluoride, sodium yttrium fluoride, ytterbium fluoride, calcium fluoride, zinc oxide. So these are what we call the matrices or the nanoparticle base, and we embed, or in sciences we dope europium, which is a lanthanide, to a certain percentage. So the idea is, again, you make the nanoparticle and you coat the surface. We call it surface engineering. We coat the surface with this material, this ligand, which can absorb light. It's a really good absorber, and it will transfer that energy to the lanthanide, so you get the light out. So that's the bottom line. All right. So we made this system called lanthanum europium fluoride and coated with this ligand. And when you shine light, like we said, it gets excited, it gets transferred to the metal, and you get the emission from the metal center. So you can see in this graph, the left side of the graph is absorption, and the right side is the red curve is the emission. You see, yes, it works. So that means we have proved that you can make a nanoparticle, coat it with the organic ligand, and it will do the Foster type energy transfer or FRET energy transfer. So this left figure shows without that coating, right figure shows with the coating. You see that it emits light. And our efficiency is not that great. It's 4%. We still can see it, but it's not that good. Okay, so you see these nanoparticles are characterized by a technique called transmission electron microscopy, where you use an electron beam to focus. You know, light microscopes are not good to detect nanomaterials. You know why? Because they're too small. So what we have to do is we have to use a transmission electron microscope. Another place I have seen a lot of physicists work on developing instrumentation and as well as studying materials using electron microscopy. I've seen a lot of colleagues or people, scientists with physics degrees. So, and physicists most of the time think, oh, it is a nanomaterial. This is kind of like a magic. How do we make it? I'll tell you, it's not that bad. It's very simple. You just get the salts, metal salts, and you get your anion salt and you mix them. The key is to control the concentration, the temperature, the time, and you get the nanoparticles. So the student who did this work got 4%. So the particles are quite big. So what she wanted to do was she wanted to make smaller particles and see whether we can enhance this efficiency, because the Foster energy transfer mechanism, the energy transfer depends on the distance from the molecule surface to the molecules. So she made some other types of nanoparticles using a high temperature method. She made some organometallic precursors and heat them to a higher temperature. You got the nanoparticles, and indeed they were small. These particles were like 20 nanometers in size. This is called scanning electron microscopy. You see these individual balls are nanoparticles. So what we do is we characterize these nanoparticles using these electron microscopy techniques. You can see when you zoom in, you can get one individual nanoparticle on the screen. And we use another technique called X-ray powder diffraction. Okay, what we do is we use an X-ray beam and we shine the X-ray beam at the material and it gets diffracted because X-ray wavelength is comparable to the atom size. And you get a certain pattern, we call it's a diffraction pattern. You see your y-axis is the intensity, your x-axis is the 2 theta. Theta is the diffraction angle. Okay, so this pattern gives you what kind of a nanostructure we have. So in this case, we call it a cubic close-packed nanomaterial, nanostructure. So we prove that we made the right crystal structure that way. This X-ray diffraction pattern can also be used to figure out the size of the crystalline. That means what is the size of one crystal dimension in this nanomaterial. So we call it the Scherer equation, and there's a shape factor, and we get the nanocrystalline size by using the wavelength of the X-ray light. If we use a copper light, it's it's 0.154 nanometers. Then we measure the full width at half maximum of the peaks. And you know the two theta value, so we can get the theta. So we can use this equation to calculate the crystalline size of these nanoparticles. So we calculated it to be 19 nanometers. It's a very tiny, small nanoparticles, what we are talking here. So again, we coat the surface of the nanoparticles with our ligand. And you see the nanoparticles are white color. They don't absorb visible light. They absorb UV. When you shine light, you see they emit red light. And this is the emission spectrum. It shows the emission at 615 nanometer. The absorption spectrum shows it absorbs UV light. And when you coat the nanoparticles with the ligand, it gets the characteristic feature of the ligand. And we can fine tune the surface coating ligand amount, and we can enhance the quantum yield. Now we are at 17%, which is a big deal for us, going from 4% to 17%, showing the first time in the world that you can do this process and you can excite the nanoparticle by using a surface coating ligand. So I think I've told you the full story here, but I'm going to show you some more examples here. Another method that we use to characterize the nanoparticles, the elemental analysis, is called energy dispersive X-ray. That you shine electrons on these high energy electrons, and it eject X-rays from inner orbitals, and those are characteristics of the element. So pretty much you can get the elemental composition here. So your x-axis is kilo electron volts. That's the energy of those X-rays emitted by inner orbitals. Your y-axis is the intensity. So here we prove that we have europium, sodium, yttrium, and fluorine. We can map these elements using these EDS, energy dispersive X-ray type techniques. You see the distribution of your yttrium to europium to sodium. You see the sodium is low, and you can count or quantify these amounts. So we measure the luminescent lifetimes. They are pretty high for these materials. That's an advantage for these materials. So now we shifted our research on to make other matrices like calcium chloride, which can be biocompatible. Biophysical fields are very demanding these days, coming into the picture. So we wanted to make some europium calcium chloride nanoparticles. We use a microwave method, like a scientific microwave, to give uniform radiation. And then we got these nanoparticles. You see all of them are the same size, very impressive method of making nanoparticles. Now, we've done a lot of work here. We've changed the initial salt concentration that would fine tune the size of the nanoparticles. We've done the coating of the nanoparticle with that ligand. You see, we can see they are glowing. They emit luminescent. So we are seeing the same concept with these materials as well. The energy transfer mechanism that we were talking about. And these particles are like 40 nanometers, and you see they have a rough surface. They are like flower-like. And this figure C, you see the lines. I don't know how clear it is. You see some areas there are lines, those lines are group of atoms. So we can now even see group of atoms using these kind of high imaging technologies. XRD, you see when you increase the doping level, that means you are introducing more europium. The peaks are shifting slightly, but it is still maintaining the same crystal structure. You see the black curve is no europium, just calcium fluoride, but blue to red, you see we are introducing certain percentage of europium, and it's shifting a little bit, but still we believe it maintains the crystal structure. Again, luminescent is shown, and we calculate the theoretical metal amounts by using some digestion techniques like ICP, and you can correlate the amounts actually in the nanoparticle. So initially you see the actual amounts are higher than what we anticipated, but when you increase the percentage, it comes to the same numbers. Then we started making nanomaterials using zinc oxide, which is a semiconductor with a wide direct band gap. And it has some biological applications too. People try to use them for antimicrobial, especially with COVID. It is a big deal again. It's used in some other applications. So we developed methods to make nanoparticles incorporating lanthanides into zinc oxide matrix. And that does the same thing. It glows when you cover it with the ligand, the photosynthesizer. Absorption is in the UV. And our quantum yields are up to 15% here, which we use to do some imaging here with some cellular imaging to show that we can image cells using these nanoparticles. What we want to do is we want to study some photophysical properties inside the cells and see how we can use them for some biological imaging of live cells. The last part is, very briefly, I want to quickly focus and show you a couple of slides on magnetic nanoparticles are a big deal. So iron oxide, Fe3O4, is rust. You know, rusting, that is useless. However, if you make a rust nanoparticle, it is useful because now we are in the nano region. These are very small nanoparticles, which we can try to use for some magnetic applications. You see they show these magnetic properties, magnetic moment with the external field change, and they are very impressive. The reason for that is these nanomaterials have a large number of unpaired electrons. If you go to europium, you have 6 unpaired electrons. Gadolinium has 7 unpaired electrons. So when you couple these magnetic moments, you get higher magnetic properties. And it emits too. So because of the europium, you get luminescence. So we call them dual modality agents. Your optical and magnetic properties are there. All right, so I think I'm on time. So we have developed synthetic methods to make these different nanoparticles. We are working on luminescent quantum yield applications, calculating them. We confirm that our sensitizer works. And for the first time, we have shown that you can coat the nanoparticles and it emits light. We've done some preliminary studies showing their applications in biological systems. And I would like to thank my collaborators, funding agencies, and my students here. And there are some Sri Lankan names as well. I want to take 1 minute, quickly show you like few pictures like I always do here. So I live in North Carolina, United States, which is a high elevation. We see a lot of waterfalls, a lot of hiking, mountains, a lot of walks people like to do. This is a big city, but I live in suburbs. I like small towns. So I kind of live in a small village. Here are some color changes that happens in October before the winter season starts. It's a nice time to go for drives, walks. Here's my university. It's kind of like in a valley. These are surrounded by mountains. These are some of my students working in the lab. Also, we have a very impressive marching band. here in my university. Some events, some football events that they were performing. And if you are planning to come to United States or to go to another country to do higher studies, if you have any questions, there also I would like to address those. If you have any questions, you can email me later as well. Just wanted to show you this last picture. Just with some humor, I want to finish this. If you ever try to go to another country, think about how we drive here compared to Sri Lanka. So you may have to learn some attitudes, disciplines as well, in addition to physics. With that, I would like to conclude. And if you have any questions, I'm here to answer. Thank you very much for this opportunity.
Thank you very much, Dr. Channa. It's a very interesting presentation and it's very impressive. If anyone would like to ask any question, please feel free to ask. In the message box also, we have several questions. One is, can we analyze the nanomaterial characteristic using Raman spectrum?
Yes, I've seen, even in my university, we've done a lot of Raman work with the gold, silver type nanoparticles. You know, those nanoparticles create plasmon resonance. Definitely, yes, we've done a lot of work with Raman spectroscopy to analyze heavy metal. Those are just metal nanoparticles. There's no anion like what I make. Like I have fluorides, oxides, but these are just the metal by itself. There's a lot of research going on right now. Huge improvements over the years of using Raman spectroscopy for analyzing plasmon resonance. And you know what I did was I was using a ligand to couple to the nanoparticle, but some other scientists are working on coupling that plasmon resonance to other things so you can do some analysis. Yes, yeah.
Yeah. Then there's another one from Tulanchen. As you said, when the region distance from the metal changes, the luminescence property change. If so, how did you check the distance from the metal surface?
That's a, yeah.
In a SEM image, as you said, how to figure out the atom assembly? Yeah.
Right. So yeah, very good questions. So the first part is, how do you check the distance from the metal surface? So it is a really challenging problem. But I haven't shown you that with the SEM, there is like STEM. You can do some tracking with the SEM, scanning electron microscopy, like you can scan through the nanoparticle in nanometer region, you can get the atom composition. Like if it's like a 5 nanometer long, you can draw a line on the nanoparticle and the instrument can go and check the atomic composition along that line and give you a graph. So that's one way to check that, to see how far the metal atoms are diffused within the crystal structure. The other thing is, what we haven't done that really, actually. What we are looking at right now is making bigger particles versus smaller particles and see whether it gives you a change. That's what you saw. But to be more precise, we can do that scanning type techniques to see how the distribution is there. In SEM images, as you said, how to figure out the atom assembly. Okay, there is a method called within the EDEX, you can get the electron diffraction using SEM as well. What I did was, what I have shown here is the electron, the quantification, meaning the amount of electrons coming out, which is related to the elemental analysis. That's what I have done. But you can do electron diffraction on the SEM as well, which gives you the crystal structure. You have to do the HKL, you know, indexing. But what we make It's well established. People know what the crystal structure is, so which is easy. You just get our diffraction pattern and you match it to the literature. So that's what we did. That's how you figure out the atom assembly. I can read the questions now. So the next one is, could I please have your email address to get some advice on my highest? Definitely, yeah. What I can do is, yeah, I can even put it in the chat box. That's not a problem. If you have any questions, you can email me. I will type it in. As you said, plasmon coupling to ligand, how crucial it is when comes to organic ligands like glutathione. So I don't know, are you talking about Raman spectroscopy? You know, sometimes it is a challenge to do Raman spectroscopy on organic molecules because the Raman intensity is very low. But what people do is they take the advantage of the plasmon resonance and somehow couple it so that you can make use of what you call the fluorescence resonance enhanced Raman. That kind of techniques can be done, can be used. That's something, it's not guaranteed. You have to play with it. You have to make it and then see. You can code the nanoparticle with the glutathione and see whether it picks up the signal. You can try it without it and then give it a try. But that's what you can try. Does the monodispersity of the nanoparticles is important for your application? Yes, because if you get polydispersed nanoparticles, that means the sizes are not the same. It is very hard to control the size, or when you do surface coating, you may have different amounts of coated on different nanoparticle. Then it's not going to be very uniform. So then we will not be able to make some conclusions. So we always want to make monodispersed nanoparticles, which is a really, really big challenge. So we've been working on years and years to make monodispersed nanoparticles. So I typed in my email address there too. What else?
Any more questions? Yeah.
How effective this when you compare to luciferase luminescence? Okay, so luciferase is, I think it's a dye, organic based dye. I will tell you that this is the reality right now. The dye molecules are still, quantum yields are very high compared to nanoparticles, most of the nanomaterials. So that's why a lot of scientists, they use dyes to do imaging, like dye sensitized solar cells you may have learned in physics. The problem with the dye is its stability is not that great compared to nanomaterials. Nanoparticles are more stable. Like if you want to do like in biology, you know, there are a lot of biophysical research groups. They are trying to use luminescent probes to track something down. Let's say you want to do a biochemical event. How do you go probe that? Like, I don't know your bio knowledge. Like, you know, if you go to a doctor or if you talk with a biochemist, if you read a book, they talk about these things like they have seen like a story. You know, we eat, your food gets here, then you make ATP, that molecule get broken down into ADP. How do they know that? They have studied those using tracing probes like dye molecules. The problem with the dye is when you trace it for a while, what it photo bleaches. So that's, it gets destroyed when you keep constantly exciting. So for mechanistic studies, I think the nanomaterials are better because even though the quantum yield is low, you can keep exciting them for a long time, for 24 hours, and they don't die. So in that aspect, nanoparticles are better, but the efficiency wise, still those kind of dyes are better.
Any more questions? I think no more questions. Let me thank Professor Channa Silva for her game. Again, I think there's a question.
Yeah, I can talk about that too. Can you please give some idea on the stability of gold nanoparticles in biological samples? Many questions. Yeah, no problem. Yeah. Okay, so it depends on the coating of the silver or gold nanoparticle. It depends on the coating. That's a big thing, and people are still working on some of these aspects. You know, you can make a gold nanoparticle, but whatever the coating makes a difference. So it's trial and error all the time. You make the nanoparticles, you coat it with something, and then you stabilize, or you just add that into whatever the biological buffer solution you are working with, aqueous, water-based, or whatever the solution you use. And then you have to measure what we call the dynamic light scattering. That is what we do. So it tells you whether they are still stable, sitting in there, or whether they are depositing at the bottom, or whether they are aggregating, because when you measure the dynamic light scattering technique, that's meaning you send a light beam and you collect the scattering light, and then you can correlate that to the particle size. So the answer to that question is, it totally depends on the size of the gold nanoparticle and what coating you have on the surface of the nanoparticle, and what is the solution you are trying to stabilize it in. I'm pretty sure somebody has developed well-stabilized methods for that. Now, I mean, I know, I see like participants here. I mean, I feel like you all, most of you are students and you do care about science. That's why you are here today. So let me put it this way. If you have any samples, if you want to analyze any nanomaterials, if you want to get some scanning electron microscope or some analysis for your project, if you can send me the nanoparticles as a solid, you can ship me, I will do that for free. The only expectation is the university, my university will want me to be part of a co-author, or like a author in your publication or wherever you present. You will be the first author, or your faculty mentor will be the corresponding author. I'm not asking a corresponding authorship, but my name should be there. That's the only expectation they have. Other than that, if you have anything, if you want to get done here for free, I can do that. If you want to send me, you can talk with the Professor Gamage or Dr. Chaturi if you want to coordinate anything like that. I'm here to help with any research you do. Thank you.
So thank you very much, Dr. Chan, again for his presentation and valuable ideas. In order to wind up our presentation, I would like to invite Joint Secretary of IPSL, Dr. Gayan Ileper, for the vote of thanks.
Thank you very much, Professor Shanta. This was the first webinar for this year, and we had a great webinar and a great start. First, I'd like to show my gratitude to Dr. Channa Silva from the West Carolina University, USA, on behalf of the Institute of Physics, Sri Lanka. It was a superb and exciting lecture, and we all had learned so much from it. It was such a detailed and well-organized lecture. Thank you very much, Dr. Channa. Next, I'd like to thank President of the IPSL, Professor Shanta Gamage, for the guidance provided for the IPSL. Also, a special thanks for Dr. Chaturi Nupearachi for introducing today's guest speaker and organizing this amazing workshop. He had been always enthusiastic and the main force behind all these guest lecture series. I also like to thank the IPSL members and the others who supported us in various aspects. For example, providing the publicity by sharing about details in their social networks. Last but not least, I like to thank all the ladies and gentlemen who participated for this event. It is your continuous interest that keep this lecture series going. Finally, I like to wish you all the best and hope to meet again in the next guest lecture. Thank you.